Hi, welcome to the Olympiad Geometry Club. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. Today we're going to talk about the geometry treasure Brocard point. This is a very special point which relates to many other special points and has many properties. For this video, I'll just introduce some very basic theorems about the Brocard based on the book of Geometry Treasure. But if you are interested in this one, in the Brocard point, you can find the relationship between this point and other special points. It's kind of like endless, right? Lots of theorems you can study about. Okay, let's just start. The first thing is we want to introduce the concept of Brocard point. The Brocard point is such a point that in the triangle ABC, let's say you can find a point P inside of the triangle ABC, which makes angle PAB equals to angle PBC equals to angle PCA equals to alpha. Okay, this is alpha, this is alpha, this is alpha. Then we call point P as Brocard point. The question is, the first question would be how to find the point P, how to find this Brocard point. Let's consider that because angle PBC equals to angle PAB. So consider about, like, we have a triangle here, and if we can find the, bear with my drawing, if we can find the circle of this triangle, right? And we want to find some angle here equals to this angle. Then we know that this line must be the tangent line of this triangle. Right? So the question is for a triangle ABC, I don't know where is this point P. How can I find it? Because we already know that B is on this circle, and also BC would be the tangent line of this circle. That means the center of the circle would be on the perpendicular line that perpendicular line of BC that passing through B, right? So we can do this. We can find the perpendicular line of the BC that passing through point B. And also we know that AB is a chord of this circumcenter. That means the center would be on the perpendicular bisector of size AB. So we can directly find the perpendicular bisector. Now we have O here, and we know that OB equals to OA, right? Based on this, we can just draw a circle. Right, we can draw this circle. I'm not going to draw the full of this circle, but you can see this would be the circle. Circle O, let's call it O1. Similarly, we can find another circle O2, which that we do the perpendicular line, that perpendicular line of AC that passing through point A. So, right. And also we find the no, I think this is wrong. perpendicular line of AB that passing through A, right? And also the perpendicular bisector of sides AC. So roughly say here, then we find it as O2. Then we can draw the O2, which is tangent on point A. Tangent with AB on point A, and then this would be that circle O2. Okay, so now we know this point P is the Brocard point that we are looking for. Why? Because BC is a tangent line of circle O1, so angle PBC equals to angle PAB. And also because AB is a tangent line of the circle O2, so angle BAP equals to angle PCA. Now we have this one equals to this one equals to this one. So we know that this point exists, and we find a way to, we just describe the way to find it. Okay, now let's consider about the property, the theorems about this Brocard point. Theorem 1. P is a Brocard point of triangle ABC. The Brocard angle is angle PAB equals to angle PBC equals to angle PCA equals to alpha. Then we want to prove this one. 1 over sine square alpha equals to 1 over sine square A plus 1 over sine square B plus 1 over sine square C. If you look at the figure, we're trying to find 1 over sine square alpha and as a function of angle A, angle B, angle C. And this function would be the summation of 3 terms. So it's obvious that we want to use these triangles and use the area, right? Let's consider about the area of triangle ABC. It equals to the area of triangle PAB plus the area of triangle PBC plus the area of triangle PCA. So the question is, how can we calculate for the area of triangle PAB? Right, the triangle PAB. So we have the area of triangle PAB equals to 1 by 2 AB AP sine alpha. Similarly, the area of triangle PBC equals to 1 by 2 BC BP sine alpha, and the area of triangle PCA equals to 1 by 2 CA CP sine alpha. Then we have half of AB AP sine alpha divided by, this is a area of triangle PAB divided by the area of triangle ABC. So we want to cancel the AB. Then we have half of AB AC sine A plus half of BC BP sine alpha divided by half of, we want to cancel this BC term, right? So BC BA sine B plus half of CACP sine alpha divided by half of CACB sine C. equals to 1. Right. Now we have sine alpha divided by sine A times AP to AC plus sine alpha to sine B times BP to BA plus sine alpha to sine C times CP to CB equals to 1. What is AP to AC? AP to AC. AP to AC. AP to AC equals to sine alpha divided by sine angle APC. What is sine angle APC? Sine angle APC is sine pi minus angle PAC minus alpha, right? And we know that PAC plus alpha equals to PAC plus alpha, that is angle A, so it equals to sine alpha to sine pi minus A, which is sine alpha to sine A. Similarly, we can get BP to BA equals to sine alpha to sine B, and CP to CB equals to sine alpha to sine C. Then we get sine square alpha to sine A square A plus sine square alpha to sine square B plus sine square alpha to sine square C equals to 1, which means 1 over sine square alpha equals to 1 over sine square A plus 1 over sine square B plus 1 over sine square C. Okay, that's the first theorem. And corollary 1, Q is the Brocard point of triangle ABC. The Brocard angle is angle QBA. Notice that now the order is different, right? Previously it was PAB. PAB is here, now QBA. So this would be, we need to find another point. Let's do it here. Now we have QBA equals to QAC equals to QCB equals to beta. And we want to prove that 1 over sine squared beta equals to these three. It's obvious that we're not changing anything, right? Because it's still that using the same method, the area of triangle ABC would be the summation of these three triangle areas, right? And it's just a QB to AB and QC to BC and QA to AC. So it's quite straightforward to prove that these two are the same, right? And based on this, we have the corollary 2. For any triangle ABC, two Brocard angles are equal. It's obvious. And corollary 3, cotangent alpha equals to cotangent A plus cotangent B plus cotangent C. Let's think about it. What we have right now, is 1 over sine square alpha equals to 1 over sine square A plus 1 over sine square B plus 1 over sine square C, right? Based on this, it equals to cosecant square alpha equals to, the equivalent to cosecant square alpha equals to cosecant square A plus cosecant square B plus cosecant square C, right? And we know that cosecant square alpha equals to cosecant square alpha equals to cotangent square alpha plus 1, right? Because this one is 1 over sine alpha, this one, like, we're trying to do sine square alpha plus cosine square alpha to sine square alpha, right? So it equals to cotangent square alpha plus 1. Then we can replace this into this term, so we have cotangent square alpha plus 1 equals to cotangent square A plus cotangent square B plus cotangent square C plus 3. Right, which means that we got cotangent square alpha equals to cotangent square A plus cotangent square B plus cotangent square C minus plus 2. Okay, this is what we get here, and we want to prove that. Notice that we want to prove cotangent alpha equals to cotangent A plus cotangent B plus cotangent C, right? We want to prove this one, but now we get this one, so we can just try to do the following. We square it, right? So let's calculate what is the square of cotangent A plus cotangent B plus cotangent C square, right? We want to find out this one. So it equals to cotangent square A plus cotangent square B plus cotangent square C plus 2 cotangent A plus cotangent A cotangent B plus cotangent B cotangent C plus cotangent C cotangent A. Right? We have this one. So to get the cotangent A, cotangent B, we can think how can we get these three terms, right? Think about this. Cotangent A plus B. What is it? It would be cosine A plus B to sine A plus B, which equals to cosine A cosine B minus sine A sine B to sine A cosine B plus sine B or cosine A, right? Sine B cosine A, right? We have this term, which equals to, we want to get cotangent A, cotangent B, right? So if we divided by sine A sine B, right? So we get cotangent A cotangent B minus this one would be 1, right? Divided by, so basically we divide sine A sine B on both the numerator and denominator. So we got cotangent A cotangent B minus 1 divided by cotangent B plus cotangent A, right? We got this one. That's a cotangent A plus B, and cotangent A plus B, which equals to cotangent pi minus C, right? And we know that cotangent pi minus C, which equals to minus cotangent C. So that means this term equals to minus cotangent C. Then we get cotangent A cotangent B minus 1 equals 2 minus cotangent B cotangent C minus cotangent A cotangent C, right? And we can move all of these back to here. Then we got cotangent A cotangent B plus cotangent B cotangent C plus cotangent C cotangent A equals to 1. Okay, now we get this one equals to 1, which means here we got cotangent A plus cotangent B plus cotangent C square equals to these plus 2 times all of these, and these equals to 1, which means we just get cotangent A plus cotangent B plus cotangent C square equals 2 cotangent square A plus cotangent square B plus cotangent square C plus 2, right? Which equals to cotangent square alpha. Then we get cotangent alpha equals to cotangent A plus cotangent B plus cotangent C. Okay, so we just prove this one. Then corollary 4. We want to prove that cotangent A plus cotangent B plus cotangent C equals to cotangent alpha is equivalent to this one. It's obvious, we just prove it. And corollary 5, we want to prove that alpha is in the range of 0 and 30 degrees. Okay. We can think about it this way. So let's see. We want to prove that alpha is in the range of 0 to 30 degrees, and it can only come from what we have here. Hold on, let me see. Let's use this one, right? We know that what we got is that cotangent square alpha equals to cotangent A plus cotangent B plus cotangent C square, right? Which is larger than or equals to 3 times of cotangent A cotangent B plus cotangent B cotangent C plus cotangent C cotangent A. Right, that's from the basic equality inequality equation. Then, because this equals to 1, which means that cotangent square alpha is larger or equals to 3. So we got cotangent alpha is larger or equals to square 3, which means alpha is in the range of 0 to 30 degrees. Okay. Now corollary 6. We want to prove that PA to B square plus PB to C square plus PC to A square equals to 1. The first thing is, what is PA to B, right? What is PA to B? Remember, we have the figure here, and we want to check on PA to B. We want to check on PA to B, PB to C. and PC2A. So PA2B, B is here, right? PA2B, we know this is alpha, this is alpha, this is alpha. So PA2B equals to sine alpha to sine angle APC. And we already know that sine angle APC is sine angle A, so it equals to sine alpha to sine A, right? So basically it's asking us sine alpha to sine A squared plus sine alpha to sine B squared plus sine alpha to sine C squared equals to 1. It's obvious because we already got this one, right? Okay, now PC2B. We want to prove that PC2B plus PA2C plus PB2A equals to 2 cosine alpha. What is PC2B? Notice it's different, right? Previously we just calculated PC2A, that's sine alpha to sine C. So what is PC2B? We want to calculate for PC2B. This is P, A, B, C, right? Let me just write it down. We want to prove that PC2B plus PA2C plus PB2A equals to 2 cosine alpha. Okay, the question is PC2B, which is this one to this one, right? This one to this one. So it equals to sine A minus alpha to sine A minus alpha, right? PC2B, that is sine this angle, which is A minus alpha to sine angle APC. Sine angle APC is sine pi minus A, which is sine A. So that is what we have here. And also we have PA2C, which is sine. So you can see from here, it must be B minus alpha to sine B, right? Let's check. PA2C is sine B minus alpha to sine B. Okay, and PB2A, which is PB2A here equals to sine C minus alpha. Right, that is PB2 sine C. Okay. Now you can see this one, we can have it as sine A cosine alpha minus cosine A sine alpha divided by sine A. Plus sine B cosine alpha minus cosine B sine alpha divided by sine B plus sine C cosine alpha minus cosine C sine alpha divided by sine C, right? And it equals to cosine alpha, actually 3 cosine alpha, right? Cosine alpha, cosine alpha, cosine alpha, minus cotangent A times sine alpha plus, minus cotangent B times sine alpha minus cotangent C times sine alpha, which equals to 3 cosine alpha minus sine alpha times cotangent A plus cotangent B plus cotangent C, right? This one is cotangent alpha. So sine alpha times cotangent alpha is cosine alpha. So 3 cosine alpha minus cosine alpha equals to 2 cosine alpha. Okay, we just prove it. And we also want to prove that PA2C times PB2A plus PB2A times PC2B plus PC2B times PA2C equals to 1. Okay, and we just proved that, PA2C, which is this one, so cosine alpha minus cotangent B sine alpha, right? So this one equals to cosine alpha minus cotangent A sine alpha, and this one is cosine alpha minus cotangent C sine alpha. Now what we want here is like PA2C, which is cosine alpha minus cotangent B sine alpha times PB2A, so cosine alpha minus cotangent C sine alpha, and plus PB2A, so cosine alpha minus cotangent C times sine alpha times PC2B, so cosine alpha minus cotangent A times sine alpha plus cosine alpha minus cotangent A times sine alpha times cosine alpha minus, right, that's PC2B and PC2A cosine alpha minus cotangent A times sine alpha. We want to prove these summation equals to 1, right? Let's expand this. Then we get cosine square alpha plus cotangent B cotangent C sine square alpha minus cosine alpha sine alpha cotangent B plus cotangent C. Right, that's the first term. And then we can list the other two. So cosine square alpha plus, right, cotangent C cotangent A sine square alpha minus, of course here is a positive sign, minus cosine alpha sine alpha cotangent C plus cotangent A, right, and plus cosine square alpha plus cotangent A cotangent B. Sorry, I think here I made a mistake, right? Say this one should be B. Yeah, cotangent B sine square alpha minus cosine alpha sine alpha and cotangent A plus cotangent B. Right? So we want to add these three terms, so that's 3 cosine square alpha plus cotangent B, cotangent C plus cotangent C, cotangent A plus cotangent A, cotangent B, these times sine square alpha minus cosine alpha sine alpha cotangent twice of cotangent B plus cotangent C plus cotangent A, right? And we just proved this one equals to 1. So we have 3 cosine square alpha plus sine square alpha, right? Minus 2 sine alpha cosine alpha. And for this one, we know it equals to cotangent alpha, right? So what is cotangent alpha? Times these two, that's 2 cosine square alpha. So it equals to cosine square alpha plus sine square alpha equals to 1. Okay, we just proved this one. And let's see. We now want to prove that B to PC plus C to PA plus A to PB equals to B to PC times C to PA times A to PB. Okay, so let's rewrite it. PC to B equals to, let me check. Yeah. PC to B equals to cosine alpha minus cotangent, oh wait. Yes, cotangent A sine alpha. That's what we got, right? That's what we got here. And PA to C, PB to A. PA to C equals to cosine alpha minus cotangent B sine alpha. Right, yes. And also PC to A equals to cosine alpha minus cotangent C sine alpha. Now we want to find actually B to PC plus C to PA plus A to PB. I'm thinking, so if we simply flip it, it would be difficult to calculate, right? Because 1 over cosine alpha minus cotangent A times sine alpha, that's difficult to simplify. So what else we can do? B to PC plus C to PA plus A to PB. And if we started from the original derivation, then it would be sine A2, sine A cosine alpha minus cosine A sine alpha. Actually, there should be an easy way to think about this problem. I'll just skip this for now. I think I derived it when I prepare for this video. Use a unique trick. I need to rethink about this one. Let's skip this for now. And corollary 8, PC to B square plus PA to C square plus PB to A square, right? That's lots of calculation as this one. So we have cosine square alpha plus cotangent square A cosine square alpha minus 2 cosine alpha cotangent A sine alpha, right? Plus cosine square alpha plus cotangent square B sine square alpha minus 2 cosine alpha cotangent B sine alpha, and also plus cosine square alpha plus cotangent square C sine square alpha minus 2 cosine alpha sine alpha cotangent C, and we want to prove that these equals to 2 cosine 2 alpha. Let's try, right? So we got 3 cosine square alpha plus sine square alpha cotangent square A plus cotangent square B, right? Plus cotangent square C and minus sine 2 alpha cotangent A plus cotangent B plus cotangent C, right? And we know that cotangent A plus cotangent B plus cotangent C equals 2 cotangent alpha. So we better write it as 2 sine alpha cosine alpha, right? Times cotangent alpha, which is cosine alpha divided by sine alpha. So we got 2 cosine square alpha here. So we still get cosine square alpha, right? And plus sine square alpha and this one. I think this one we just calculated it. Let me show you. Yeah, we just calculated it here, right? Which is cosine square alpha. This cotangent square alpha. This is cotangent square alpha minus 2. That's these 3, right? Cotangent square A plus cotangent square B plus cotangent square C. So, yeah. So it's sine square alpha times cotangent square alpha minus 2. Right, and then we got sine square alpha times cotangent square alpha. That is cosine square alpha, twice of the, that is cosine square alpha, right? So we got twice of cosine square alpha minus 2, which is twice of cosine square alpha minus 1. So it is 2 cosine 2 alpha. Let me just give me 1 second to confirm. I think I did the right thing, but just to confirm. Yeah, I think so. Yeah, I think so. It's just lengthy. Okay. Let's see the next one. Alpha is the Brocard angle of the triangle ABC. S is the area of triangle ABC. Then we want to calculate for cotangent alpha equals to this one. So the question is how to calculate for cotangent alpha, right? Cotangent alpha is cosine alpha divided by sine alpha. What is cosine alpha? What is sine alpha? Cosine alpha comes from cosine alpha equals to, actually, let's do it this way. So if we draw the figure and let's think about the cosine alpha. So we have point P here. This is alpha, this is alpha, this is alpha. So cosine alpha comes from the cosine law, which we can define which we can define the length of the PA-PB-PC. So we have y squared equals 2x squared plus c squared minus 2cx cosine alpha, which means cosine alpha equals 2x squared plus c squared minus y squared divided by 2cx. Right, that's for this one. Also, we have cosine alpha equals 2. We just used this triangle, right? We can use this triangle, then we get it's a squared plus y squared minus z squared divided by 2ay. And also cosine alpha equals 2 b squared, hold on. Yeah, b squared plus c squared minus x squared divided by 2bz, right? That's a cosine alpha. And sine alpha equals 2. So sine alpha can be calculated from the area. So sine alpha, which means that we can use the area of triangle APB equals 2 half of xc sine alpha, which means sine alpha equals 2s APB divided by xc. Right, that's sine alpha. Which means we can replace xc by sine alpha. Oh, we can just do this, right? So let's do this. Cosine alpha equals 2. No, actually I don't want to do that. Let's just replace xc into here. So we got cosine alpha equals 2x squared plus c squared minus y squared divided by 2cx. So 2, the area of triangle APB divided by sine alpha. Right. So we got cosine alpha. Cosine alpha equals 2. Let's do this way. Cosine alpha times 2s APB equals 2x squared plus c squared minus y squared. Right? We just move this here. So we have the sine alpha actually on the denominator. So move here, we got cosine alpha and then times 2s triangle APB equals to this one. Similarly, for the other two terms, we can get cosine alpha times 2 area of triangle. So let's say APB, right? For this one would be this one, the area of triangle PBC equals 2 a squared plus y squared minus z squared. And also cosine alpha times the area, twice of the area of triangle PCA equals 2 b squared plus c squared minus x squared. Then we can sum these three terms. We can have cosine alpha times twice of the area of triangle ABC equals 2. So you can see x, y, y, z, z, right? So it equals to a squared plus b squared plus c squared, which means cosine alpha equals 2 a squared plus b squared plus c squared divided by 2s. Wait. here is 4s. Oh, I see. Here would be twice of xc, but here we have another 2 times xc, right? So here would be 4, this would be 4, this would be 4, this would be 4, and here would be 4. Okay, that's a cotangent alpha. And then we want to calculate for sine alpha. For this sine alpha is pretty straightforward because, oh, actually, no, let's see, sine alpha. We want to calculate for sine alpha. Right, we want to prove that sine alpha equals 2s2 squared a squared b squared plus b squared c squared plus c squared a squared. And you can see cosine alpha directly comes from these two, right? The product of these two, that's a cosine alpha. So cosine alpha is easy. Let's think about the sine alpha. How can we get the sine alpha? Right, question is how can we get the sine alpha? Sine alpha comes from the area xc times sine alpha, that's the area of this one, and also ya, the area of this one, zb, the area of this one. If we add them together, then we got sine alpha bx, xc, ya, and zb. But from there, we got nothing. How can we calculate for sine alpha? Yeah, let's do this way. If you look at the sine alpha, we already got 1 over sine square alpha equals 2. 1 over sine square a plus 1 over sine square b plus 1 over sine square c, right? So we just need to prove that a square b square plus b square c square plus c square a square 2 4s squared equals 2. 1 over sine square a plus 1 over sine square b plus 1 over sine square c. We just need to prove this one. Hope that makes sense to you, right? Because that's sine square alpha. 1 over sine square alpha, right? 1 over this one. We just need to prove this one. And this one is obvious because AB sine C is 2s, right? So a squared b squared divided by 4s squared, that's sine square c. Similarly for this one is sine square b, this one is sine, this one is 1 over sine square a, and this one is 1 over sine square b. So this is true, which means that sine alpha is this one. And then cosine alpha is a product of cotangent alpha and sine alpha. Okay, theorem 3. P is a Brocard point of triangle ABC. We want to calculate for the distance of PA, PB, and PC. So basically, we want to calculate this x, y, and z. Right, we want to calculate this x, y, and z. So think about, let's think about x. If we want to calculate x, then what we have? We have y, we can calculate the x squared by the y squared, c squared stuff, and then find the x, right? And do we have better solution to find x? Because that's a cosine law, right? And if we use a sine law to find x, then we have x2b, right? x2b equals to sine alpha to sine a, which means x equals to b to sine a times sine alpha, right? We have the sine alpha already, right? Let's see. Sine alpha equals to 2s2 squared a squared b squared plus b squared c squared plus c squared a squared, right? We have the sine alpha already. And then we know x equals to b to sine a times sine alpha. So means x equals to 2sb divided by sine a squared these things, right? So it equals to 2s divided by sine a and times b. 2s divided by sine a. 2s divided by sine a, which is bc. So we got b times this b, so b squared c divided by square root of this one. Right? We're done. So if you look at here, that's a PA. And we can, which is x, we can calculate by the sine law. So it's very easy to get it. And corollary 1, AP to BP to CP equals 2 B squared C to C squared A to A squared B, which is obviously we can get it. Let DAB, DBC, DCA represent for the distance from P to AB, BC, CA. Then we have the distance ratio. It's still this ratio. Why? Because it's just PA, PB, PC times sine alpha, right? The sine alpha would be the same, so the distance would be the ratio of PA to PB to PC, so that is true. And corollary 3, the area of triangle PAB to the area of triangle PBC to the area of triangle PCA equals to this one. This one, notice that it's just adding C on the first term, adding A on the second term, adding B on the third term of this ratio, right? Why? Because we can think about it's just the distance ratio times the size ratio, which is this one is B squared, this one to this one to this one, that's B squared A to C squared, B squared C to C squared A to A squared B, and times C times A times B respectively, then we get this one. So it's straightforward. Extend AB, BP, CP to the sides intersecting on point DEF. So if we do this, right, this would be F, D, E. Now we want to find that AF to FB. AF to FB. AF to FB would be the area ratio of the triangle APC to triangle BPC, right? The area ratio of APC to BPC. So the APC to BPC would be these two, right? BPC, APC, these two. And these two, we can cancel out A squared, right? So AF to FB, that's APC to BPC. APC is this one, so it's B squared to C squared. And the rest part will be the same. Okay? Now the interesting part. The theorem for P is a Brocard point, G is the centroid of triangle ABC. Then we want to calculate for the GP. Right. It looks like lengthy, it looks like impossible, but if you recall our derivation in the Sturt theorem video, we calculated that for the any point on the plane, right, P, if we know that PA, PB, PC, then we can calculate for the GP with a formula. I'm not going to calculate all of these lengthy stuff, but I provide the method, right? That's exactly the same method. It's just a calculation. Okay. Today we briefly introduce the Brocard point, and we will talk about the properties of the Brocard point in the next video. I hope you like this one. It's just the very basic properties of the Brocard. I think we will see it when we solve some problems. Okay, that's it. I hope you like this video. See you in next one. Thank you.